Okay, let's begin our next meeting. Today, our guest is Professor Mark Groves from Saarland University. Please, Mark.
Thank you. So I'm going to play you a video of my talk, which means if you have questions, please save them until the end, because I won't be able to answer them until the end. And let me know if it doesn't work. Okay, so I'm going to mute myself and then play the video. Today, I would like to talk about some joint work on three-dimensional water waves with Boris Buffoni from Lausanne and Eric Valleen from Lund. Let me begin by outlining the version of the water wave problem in which I'm interested. The sketch shows a three-dimensional perfect fluid, so water, which is bounded above by a free surface, given as the graph of a function eta of the two horizontal spatial coordinates x and z and time t. The fluid is not bounded below, so I'm talking about water of infinite depth. We model the water as homogeneous, incompressible and inviscid, and assume an incompressible fluid flow, so that we can write its velocity field as the gradient of a scalar velocity potential phi, which is harmonic in the fluid domain. We have the asymptotic condition phi y goes to 0 as y goes to minus infinity. This is the condition that the vertical component of the velocity vanishes at great depth. And then we come to the interesting part of the water wave problem. There are two nonlinear boundary conditions at the free surface. Here they are. The first is the kinematic boundary condition. This is the condition defining the free surface. It says that no water passes through this free surface. The second is the dynamical boundary condition. This is the condition expressing balance of forces at the free surface. It says that the jump in pressure across the free surface from internal fluid pressure to atmospheric pressure is proportional to the curvature of the free surface. The constants here are g, the acceleration due to gravity, and sigma, the coefficient of surface tension. Now, I've already hinted at this, but let me now say explicitly that there are two main difficulties in the water wave problem. Firstly, it is a free boundary value problem. You do not know the function eta, defining the free surface in advance. You have to find it as part of the solution. And secondly, you have these two very unpleasant nonlinear boundary conditions at the free surface. Now let me clean up the equations by introducing dimensionless variables, which allows me to normalize sigma and g to 1. And today I'm particularly interested in traveling waves. Those are waves which move in a fixed horizontal direction with fixed speed without changing shape. Now, without loss of generality, we can assume that the direction in which they move is the x direction. That's because the equations are rotationally invariant in x and z. So traveling waves are waves which depend on x and t only through the combination x minus ct. C is the wave speed. When I make that ansatz, the t derivatives in the equation change to minus c times x derivatives. Now, more specifically, I'm interested in solitary waves, sometimes called fully localized solitary waves. Those are non-trivial traveling waves which decay to 0 at large distances in all horizontal directions. Now, here are some sketches of solitary waves which I think exist. The arrow shows the direction in which they propagate, so this is the x direction. And these are actually small amplitude, long waves. I've altered the scales so that you can see their main features clearly. So the main features are exaggerated here. And the main features are as follows. The waves are not radially symmetric, but they are symmetric in the direction x of propagation and in the transverse direction z separately, and I'll call them symmetric. So in this talk, symmetric means symmetric in x and symmetric in z. The waves decay in an oscillatory fashion in the direction of propagation and monotonically in the transverse direction. And as you can see, the main feature of the wave at the top is the central point of elevation, while the main feature of the wave at the bottom is the central point of depression. The obvious question here is, of course, why I think waves of this particular form exist. After all, if I didn't have any additional information, it would be a good guess to think that waves of this particular specific form exist. And of course, I have reasons, and there are two in particular. Firstly, there are numerical computations of waves of this form, particularly by Parau, Vandenbroek and Cooker in 2005. And secondly, I have a heuristic argument which predicts their existence. This is perhaps more relevant for the talk today, and we'll come back to that heuristic argument a little later. But first, I would like to reformulate the water wave equations themselves to overcome the first difficulty, which was the variable fluid domain. Now, there is a method of overcoming this problem which was popularized by Craig and Sulem in the early 1990s, although it had also been used in a slightly less convenient form by Sakharov in the 1960s and Benjamin in the 1980s. Craig's idea was to use a Dirichlet-Neumann operator. Now, on the left, you can see a boundary value problem in which the fluid domain, that is the function eta, is fixed, and Dirichlet data for phi is specified at the free surface. Here I have phi at the free surface is equal to xi. Xi is given Dirichlet data. Now, the Dirichlet-Neumann operator for this problem is defined as follows. You solve the boundary value problem for phi and compute its normal derivative at the free surface. The Dirichlet-Neumann operator is the operator which maps xi to this normal derivative. In other words, the Dirichlet data to the corresponding Neumann data. Obviously, the operation depends on the free surface or upon eta. So the notation here is g of eta of xi. And you can see that I also have a normalizing factor of the square root of 1 plus eta x squared plus eta y squared here. G depends non-linearly upon eta, but linearly upon xi. The normalizing factor isn't really necessary as part of the definition, but it makes some other calculations easier later. Now, using the Dirichlet-Neumann operator, I can reformulate the kinematic and dynamical boundary conditions in the water wave problem in the form you see here. I've written xi for the trace of the velocity potential at the free surface and eliminated all its normal derivatives using the Dirichlet-Neumann operator. So the variables in these equations are now eta and xi, and the equations are completely equivalent to the water wave problem, because if I can solve these equations, I can just recover the velocity potential in the interior of the fluid domain by solving the boundary value problem shown above. So we've removed the difficulty of the unknown boundary. Eta and xi are now just functions of x and z, but we've created a new difficulty. The Dirichlet-Neumann operator appearing in these equations is a non-local function of xi. To calculate it, we actually have to solve a boundary value problem. And that is the Sakharov-Craig-Sulem formulation of the water wave problem. Now, we can of course look for traveling waves. So let's make the traveling wave ansatz again and again. The d by dt changes into minus c d by dx. And there's actually one more thing that we can do with these equations. We can eliminate xi from them completely and reformulate the whole thing as a single equation for just eta. And that is relatively easy to do. If you look at the first equation, you can solve it for xi. Xi is just minus c g eta to the minus 1 of eta x, at least formally. And when you insert that formula into the second equation, you get a single equation for eta, which I'm now showing you. I've written it as script k minus c squared script L is equal to 0, and here are the definitions of script k and script L. In script L, instead of writing g to the minus 1, I've replaced it by k and L. The difference here is that k has a derivative with respect to x outside, while L has a derivative with respect to z outside. It's just a bit more convenient to work in this fashion. So k and L are sort of Neumann-Dirichlet operators. The difference is that for k you differentiate afterwards with respect to x, and for L you differentiate afterwards with respect to z. Okay, so what we would like to do is to find a fully localized solitary wave solution to the problem which is written at the top here. Script k minus c squared script L is equal to 0. In other words, a non-trivial solution eta which goes to 0 as k and z go to infinity. What I'd like to do in the rest of this talk is to focus on three aspects of this problem. Firstly, to persuade you that the formulation written down here, script k minus c squared script L is equal to 0, is rigorous. Specifically, that script k and script L are actually analytic functions of eta in a certain sense. So we really can work with this formulation of the water wave problem. The derivation was up to now formal. I'd like to show you that these are well-defined functions. I won't emphasize functional analysis, just the method, which is really easily understood. Secondly, I'd like to show you a heuristic argument, which I've already hinted at, which predicts the existence of a fully localized solitary wave, the solitary waves I showed you, in fact. And finally, I'd like to show you how to make that heuristic argument rigorous. So let's first come to the functions script k and script L, and start with a lemma concerning the functions k and L at the bottom here with these Neumann-Dirichlet operators. So I claim that k and L actually depend upon eta and psi analytically. Analytic at the origin means in a neighborhood at the origin, or in other words, that you can express these functions as convergent Maclaurin series. Now, the main point here is that they depend analytically upon eta. The dependence on psi is linear, so it's not so exciting. I've written down the function spaces in which the dependence is analytic, that is, the function spaces in which the Maclaurin series converge. You don't need these details to follow the argument which is just coming. I've just given them in case you're interested, and so that you know I'm doing everything rigorously and there's no funny business here. And as you can see, the spaces are just standard Sobolev spaces. Eta in particular lies in the standard Sobolev space H3, and the other function spaces are then just standard Sobolev spaces of fractional order, defined, for example, using the Fourier transform, in other words, the Bessel potential. Now, the corollary to this lemma is, of course, that the functions script k and script L will also be analytic at the origin. And again, I've written down the function spaces for that. They are just standard functions, standard Sobolev spaces. Okay, so how would you actually prove that those operators k and L, those Neumann-Dirichlet operators, depend analytically upon eta and psi? Well, let's take a look at them in more detail. Here they are, written down in terms of boundary value problems. Remember that they are actually defined in terms of the inverse of a Dirichlet-Neumann operator. And here, instead of writing g eta to the minus 1, I've actually written down explicitly the boundary value problem that you have to solve in order to calculate them. So you solve this Neumann boundary value problem for phi, calculate its trace at the free surface, and then take either minus the x derivative or minus the k derivative, depending on whether you want to calculate k or L. But this is still a difficult thing because the domain still depends upon eta, again in a presumably complicated way. So how to resolve this difficulty? Well, the cheapest way is simply to use a transformation which maps your unknown fluid domain, which I've called sigma eta, into a known domain sigma, which here is just the lowest half space. You can do that by introducing a new vertical variable y primed, which is just y minus eta. You see, if y is less than eta, then y primed is less than 0. So this change of variable maps the unknown domain into a fixed domain. And then you introduce a new dependent variable u just by substituting y is equal to y prime plus eta into the old variable phi. Make this change of variable in the boundary value problem, and you get a new boundary value problem for u. And here it is, written down explicitly. It's posed in the lower half space. It's a linear elliptic boundary value problem for u. But looking at the formulae for f1, f2 and f3, we see that the coefficients are nonlinear functions of eta. So we have changed a boundary value problem in a variable domain, which depends implicitly upon eta through the boundary, to a boundary value problem in a fixed domain, which depends explicitly upon eta through the equations themselves. Obviously, we can define k and l in terms of the solution to the new problem. Just substitute phi as a function of u into the definitions of k and l, and you get the formulae I've written down here. Now, obviously, if I can show that the new boundary value problem, the boundary value problem for u, is solvable, and its solution depends analytically upon eta and psi, then k and l will also depend analytically upon eta and psi, because they are just derivatives and traces of u, in other words, linear functions of u. So the issue is how to prove that the new boundary value problem has a unique solution which depends analytically upon psi and eta. Okay, so let's do the following. Let's now look at a simple linear boundary value problem, which I get by replacing the functions f1, f2 and f3 of eta and u, which we just had, by any functions f1, f2 and 3 of the independent variables x, y and z. Now this is a simple linear boundary value problem, and it's a simple exercise in linear elliptic boundary value problems to show that this problem has a unique solution for every choice of f1, f2, f3 and psi. Unique here meaning unique up to additive constants. You see, this is a Neumann boundary value problem, so obviously if I have a solution I can always add a constant to it to get a new solution. And the function space I've written down here, this h3 star, star means that functions are only defined up to an additive constant. Okay, so let's call the solution of this problem S of f1, f2, f3 and psi. Now, that problem is related to the problem I had on the previous transparency simply by replacing f1, f2, f3 by the specific f1, f2, f3 as functions of eta and u, which we were looking at. So what we would like to do is to find a function u with u is equal to s of f1, f2, f3, xi, where f1, f2, f3 are the functions of eta and u from the last transparency, because that is just the statement that u solves the boundary value problem from the previous transparency. In other words, we want to find zeros of the function t, which is given by u minus s of f1 eta u, f2 eta u, f3 eta u, and psi. So how would we do that? Well, we notice that these mappings, f1, f2, f3, are analytic functions of eta and u. You basically just look at them to see that this is the case. And that means that t must be an analytic function of u, eta and psi, because it's just a linear function of f1, f2, f3 minus u. Next, you notice that replacing eta and psi with 0 in the boundary value problem gives you 0 at a solution. So t of 0 is 0. And taking the derivative of t with respect to the first component, which is u, and evaluating it at 0 gives the identity mapping, which is invertible. So now we have a known solution at the origin, and the derivative with respect to the first component at the origin is an isomorphism. And now you're in a situation which you know from elementary analysis. You can apply the implicit function theorem, the analytic version of it. It tells you that you can solve locally for u as a function of eta and psi, and this function depends analytically upon eta and psi. So we've shown that we can solve our boundary value problem for u, and we get an analytic function of eta and psi, which is exactly what we wanted. Then k and l obviously depend analytically upon eta and psi, because they're just derivatives and traces of u, in other words, linear operations on u. This is a very simple argument which shows that our operators k and l depend analytically upon eta and psi in a neighborhood of the origin. I know more sophisticated arguments which give you information about the size of the radius of analyticity and so on, but they're not necessary in this simple setting. Now, in our formulation of the water wave problem, it means that the operators script k and script l are also analytic functions of eta in a neighborhood of the origin. So I hope I've persuaded you that the equation star is a valid equation. The left-hand side is an analytic function of eta in a neighborhood of the origin in its function space H3. And we can study this equation now in a rigorous fashion. Okay, so let's now come to the heuristic argument for the existence of fully localized solitary waves, which I spoke about earlier. However you formulate the water wave problem, it is a nonlinear dispersive equation. And you know from the first course on waves you do at university that the first thing you do when confronted with a nonlinear dispersive equation is to examine its dispersion relation. So let's do that for star. Let's see when the linearized problem admits a sinusoidal wave train. To do this, you linearize star, you seek a solution of the form cosine of k1x, and you see what the relationship between c and k1 is. You can work it out explicitly. Here it is. C squared is k1 plus 1 over k1, and here's the plot of it. You see it has a unique global minimum at k1 is equal to 1, and the value of c squared there is 2. Now then, if you ask an applied mathematician who does modeling, he would say to you, well, if I have a dispersion relation like that, there is a particular ansatz which I can make, which usually leads to a universal model equation. And the ansatz is the following. You take your wave speed and you introduce a small parameter by writing the wave speed as slightly less than its global minimum. So you can see here I have written c squared as 2 times 1 minus epsilon squared, so that the wave speed now is slightly less than the global minimum of 2. And then you expand eta in the following form. Now, the main part, the order epsilon part here, is a slow modulation of a periodic wave train with wave number 1. This is the wave number at which the minimum of the dispersion curve is attained. Zeta 1 depends upon x and z through the scale variables capital X and capital Z, and this means that we have a slow modulation of a periodic wave train with wave number 1. At order epsilon squared, you put second harmonics, in other words, two wave interactions which come from the first order terms. So you can see there are terms which don't depend upon little x, and there are terms which wave numbers 2 and minus 2. And then you have order 3 terms, those are order epsilon cubed, which are third harmonics, order 4 terms, which are fourth harmonics, and so on. You substitute all this into star and equate terms of equal powers of epsilon. At order epsilon, you recover the dispersion relation, so that's automatically satisfied. At order epsilon squared, you find that you have to determine zeta 2 as a function of zeta 0 in order to satisfy the equation. And at order epsilon cubed, you get a compatibility condition which forces zeta 1 to satisfy this equation. This is the stationary nonlinear Schrödinger equation with a cubic focusing nonlinearity. So let's take a closer look at this equation. The most important fact here is that it has a unique symmetric positive solution zeta star, which decays exponentially in x and z. In other words, a localized solution. symmetric means again symmetric with respect to x and z. Now you can find an exposition of that result together with all the references in the literature leading up to it in the book by Sulem and Sulem called Nonlinear Schrödinger Equation. Obviously, I can take the solution zeta star and multiply by e to the I theta for any value of theta, and this will also satisfy the equation. The equation is rotationally invariant with respect to the argument of zeta. So when I take zeta star e to the I theta and put it back into the ansatz we made for eta, we'll get, to leading order, a family of solitary water waves. Our ansatz therefore predicts the existence of a family of solitary water waves parameterized by theta, and two of them will be symmetric. Those are the ones with theta equal to 0 and theta equal to pi, or, if you prefer, the ones generated by zeta star and minus zeta star. And here they are. Here's a sketch of them, and you'll recognize that they are the waves which we looked at earlier. So this is the heuristic argument for the existence of such waves. Now, before I show you how to make that rigorous, let me just talk a little bit about some computational aspects. Obviously, I needed to do this expansion in powers of epsilon, which meant I had to do expansions of script k and script l in powers of eta. Essentially, I had to expand them up to cubic order. So how would you expand script k and script l in powers of eta? Well, you know that they're analytic functions of eta, so the existence of the expansions in principle is not an issue. But practically, how would you compute them? Well, script a isn't so difficult. Here's the actual formula for script k, and you can see it's just a simple thing to calculate its expansion. And indeed, here's the linear term, the quadratic term is 0, and here's the cubic term. Now, it's a bit more fun, of course, to compute the expansions of L, because L depends upon those Neumann-Dirichlet operators K and L, which we were talking about earlier. Now, we already know that K and L are analytic functions of eta, so we could expand those abstractly in series. And you see here on the left, I've got K written as K0. This is the part which doesn't depend upon eta, plus K1, which depends linearly upon eta, plus K2, which depends quadratically upon eta, and so on. And similarly for L on the right. They're all linear functions of psi. And when you insert these formulae into the formula for script L, you can calculate L1, L2, L3, script L1, script L2, script L3. But it's really not much good because we've still got those abstract operators K0, K1, and K2 there, so we do need to work a bit harder here. Now, in fact, you can find explicit formulae for K0, K1, K2, L0, and so on by remembering how you constructed the operators K and L. Remember that they are traces of the solution to a boundary value problem which itself depends analytically upon eta. So what you do is to write the solution U to that boundary value problem as a series in eta, substitute this ansatz into the boundary value problem, and equate equal powers of eta. This gives you a sequence of boundary value problems which you can solve recursively, and in this fashion you can determine the terms in the expansion of U recursively, and those give you recursive formulae for the terms in the expansion of K and L. So let's take a look at them. Here are the formulae for K0 and L0. They're Fourier multiplier operators. K0 is given by taking the Fourier transform of psi, multiplying it by K1 squared over K, and taking the inverse Fourier transform. So here, K1 and K2 are the Fourier variables associated with x and z, and K is the vector K1, K2. L0 is given in the same way. Here you multiply by K1, K2 over K. And finally, I've introduced a third operator, M0, here for completeness. Its multiplier is K2 squared over K. Now, working recursively, you can get the formulae for K1 and K2 given here, and you can see that they express K1 and K2 in terms of K0, L0, M0, and derivatives with respect to x and z. Now there's one feature of this which I'd like to point out before we go any further. If you look at these formulae, you'll see that K0, L0 and M0 all lose one derivative. If you look at K0, you see you've got K1 squared divided by K, so essentially you're multiplying by a factor of K, which causes a loss of one derivative. Similarly for L0 and M0, they both lose one derivative. Now, looking at K1, you see that that formula loses two derivatives. You differentiate twice or apply K0 or L0 twice. Similarly, K2 loses three derivatives. Now, this is typical when you derive recursive formulae in this fashion. With each recursive step, you lose one more derivative. These formulae are good for computation, but the fact that you lose derivatives means that you cannot use formulae like this for actually proving convergence of the series. You have to use more global methods like the one I discussed earlier. Nevertheless, for formal calculations, it's fine. And let me just show you how the terms in the expansion of script L look. Here are the linear, quadratic and cubic terms, which are given by the Fourier multiplier operators K0, L0, M0, and then derivatives with respect to x or z. Now, one more thing to say here is that it's actually rather easy to derive the nonlinear Schrödinger equation once you have the expansions of script K and script L. So classically it's done directly from the original formulation of the water wave problems in terms of eta and the velocity potential phi. You can find this calculation, for example, in the 1979 paper by Ablowitz and Seeger, but in my opinion that's computationally more difficult, meaning that the possibility of error is much greater. Okay, so now I'd like to show you how to make this process rigorous. And the motivation is again the leading order part of the ansatz which we just made when we derived the nonlinear Schrödinger equation. So here it is, the slowly modulated periodic wave train with wave number 1. Now, you stare at that ansatz and ask yourself what it's telling you. Well, it's telling you that the Fourier transform of eta is concentrated at the points k1 is equal to 1 and k2 is equal to 0. This is because of the factors e to the I little x and e to the 0I little z, which is equal to 1. So what you should do is to split eta into two parts. One whose Fourier transform is really concentrated near the points plus or minus 1, 0 in Fourier space. That's where the action is. And then a remainder part. And this is how I've done it. Chi is the characteristic function of the set shown in the diagram, which is made of two disks of small radius centered at the points plus or minus 1, 0. Eta 1 is constructed by taking the Fourier transform of eta, multiplying by the characteristic function of that set, and then taking the inverse Fourier transform. That's what the operation chi of d means. So the Fourier transform of eta 1 really is concentrated near those points. Its support lies in the set you can see there. And eta 2 is the remainder of eta. Now we look at the equation itself, which is script k eta minus c squared script l eta equals 0. Here it is. I've put c squared is 2, 1 minus epsilon squared as before. I've written eta 1, eta is eta 1 plus eta 2, according to the splitting which is written above. And then I've used the same procedure on the equations themselves, on the equation itself. I've split it into two parts by multiplying by chi of d and then 1 minus chi of d. Now, when you look at those two equations, you find that you can actually solve the second equation for eta 2 as a function of eta 1. And inserting this into the first equation, you get a reduced equation for eta 1. Now, this is a bit like the Lyapunov-Schmidt reduction. You split your variable into two parts, one of which captures the behavior in which you're interested, and another one which is subservient to it. You determine the latter as a function of the former, and this gives you a reduced equation. Okay, so this is then the reduced equation for eta 1. And again, we motivate ourselves by the scaling written at the top of the transparency. We do the same scaling on eta 1 by introducing a new variable zeta, and making that substitution into the reduced equation for eta 1 I just showed you. You do a lot of calculation and the result is a final reduced equation for zeta, which I'm now going to show you in all its glory. Here it is. It is the equation star. This is the final reduced equation for zeta. Now, this is a so-called full dispersion, stationary, nonlinear Schrödinger equation. And I think I should talk you through it a little bit. So, full dispersion here means that the linear part of the original equation has not been approximated. The linear part of this equation is the same as the linear part of the equation k eta minus h squared script L eta is equal to 0. Put that another way, it means that the dispersion relation of star is the same as the dispersion relation of the equation we derived it from, in other words, the water wave problem itself. And here you can see again that the linear part is defined by a Fourier multiplier operator. Now I've got this chi0 of epsilon d. What does that mean? Well, remember that the support of eta 1 in Fourier space was contained in two small disks centered upon plus and minus 1, 0. But the scaling we've done here moves this support. Zeta has support in a disk centered on the origin of radius 1 over epsilon. This is why it's now chi0 of epsilon d. Chi0 is the characteristic function of the unit disk. The remainder term is estimated in the function space h1, and the underscore notation means that the remainder term is of order zeta and its derivative is of order 1. Loosely speaking, one can differentiate this order of magnitude estimate. At the bottom here I've mentioned the function space. Zeta belongs in a ball centered at the origin in this space, which is obtained from h1 by multiplying its elements with the appropriate cutoff function in Fourier space. And here's a slightly technical comment related to that. It's actually easier to replace zeta with the cutoff applied to zeta in the equation and work in the fixed function space h1. Now the two approaches are completely equivalent, but analysts of course would prefer to work in a fixed space rather than in a function space which depends upon the parameter epsilon in the problem. And one final comment about this equation. To compute it, I of course use the expansions of script k and script L I showed you earlier, but I do not have to worry about the loss of derivatives in the recursive formulae. This is because eta 1 and zeta have compact support in Fourier space, so they are in fact smooth functions of x and z. I can differentiate them as many times as I want. Now of course you might say, and I'd be surprised if you don't, that star is a terrible equation. It doesn't look like we can do much with it. But in fact, the point is that in the limit epsilon goes to 0, it's an equation we've seen before. It's the stationary nonlinear Schrödinger equation. So we have a reduced equation star depending on epsilon, and when epsilon equals 0, it's an equation we understand well. And this is the key to the matter. We'd like to do a perturbation argument. So here comes the conclusion. Think back to what we know about the nonlinear Schrödinger equation. It has two symmetric solutions, plus or minus zeta star, which decay exponentially to 0 as x and z go to infinity. And in fact, these solutions are in the class of symmetric solutions. Symmetric means invariant under the transformations you can see here, changing x to minus x and zeta to its complex conjugate, and changing z to minus z. Non-degenerate means that the linearization of the equation at those solutions has a trivial kernel in this class of functions, and that was proved by Chang et al. In 2007. Now the reduced equation star, that's the difficult-looking equation on the previous transparency, has the same symmetry. It's also invariant under the same transformations, and that's of course inherited from the symmetry of the original problem, which is invariant under x goes to minus x and z goes to minus z. So now I think you can see what you have to do. You have non-degenerate solutions, so you just apply an implicit function theorem argument in the space of symmetric solutions. You thus find two families of symmetric solutions to the reduced equation star, which are parameterized by small values of epsilon and coincide with plus or minus zeta star at epsilon is equal to 0. And tracing back the various transformations, of course, yields the two families of symmetric solitary water waves which are advertised back at the very beginning. So this is the rigorous justification of the heuristic method which I showed you. And in some sense also, it also tells you the correctness of the heuristic method. Now, as an aside, I'd like you to note that this is actually a self-improving theory. The cubic nonlinear Schrödinger equation has other localized symmetric real solutions. In fact, there's a whole family parameterized by their number of zero-level curves. That's a result of Strauss back in 1977. And if you could show that those solutions are degenerate in the same sense as zeta star, then the theory above would apply and give you further families of fully localized solitary water waves. So it gives you a framework for establishing the existence of further families of fully localized solitary water waves. Now, let me finish with some remarks on the size of the solitary water waves that we have found, because there's an interesting issue here. Remember what we did? We decomposed eta into two parts, eta 1 and eta 2. We solved for eta 2 as a function of eta 1, applied the nonlinear Schrödinger scaling to eta 1, and found a solution for zeta which is well approximated by plus or minus zeta star. Now then, that means that the L2 norm of eta is approximately the L2 norm of eta 1, and that is to leading order the L2 norm of zeta. This is just a calculation, and that again is approximated by the L2 star or the L2 norm of zeta star. The supremum norm of eta, on the other hand, is approximately the supremum norm of eta 1, which is of order epsilon. So this tells you that the waves have small amplitude, in other words, small supremum norm, you can see it's order epsilon, but they have finite energy, meaning finite L2 norm. You can see that's the L2 norm of zeta star. So in fact, we've found waves which have small amplitude but finite energy. Now, that observation actually has consequences for our theory, which I'd just like to point out. Remember that our basic space for eta is H3, and it is not sufficient to work in a small ball centered on the origin in our space, as our solutions have finite L2 norm. We have to work in a neighborhood of the origin which is big enough to include our solutions. And there's one place in particular where you have to be careful. Remember I showed you that the Neumann-Dirichlet operators were analytic in the origin of in H3? Well, I gave you a very simple argument which showed that they were analytic at the origin, meaning this argument tells you that there's some radius of analyticity, which might be small, in which the functions are analytic. But this result isn't quite enough because the radius of analyticity might be smaller than the amplitude of the solutions we're trying to find. Now, in fact, the argument I used also showed that the Neumann to Dirichlet operators are analytic at the origin in the larger function space Z, shown here. In Z, for membership of Z, we essentially split eta into the two parts, and we require eta 1 to be bounded in the supremum norm and eta 2 to be in H3. Now, in fact, H3 is continuously embedded in Z, and open balls in Z are neighborhoods of the origin in H3. So, if the radius of analyticity of the Neumann-Dirichlet operators in Z is M, the corresponding neighborhood of the origin in Z allows eta 1 to have finite H3 norm but small supremum norm. And that's exactly the situation for the waves that we're trying to find. So this is the way to solve that problem. And of course, once you've solved the problem for the analyticity of the Neumann-Dirichlet operators in this way, it's very careful when going through the theory to make sure that you stay within the correct open ball in Z at all times, because only there are your estimates valid. And I've summarized that in the sentence at the end, which says it's important to do careful bookkeeping. Okay, well, that's pretty much all I wanted to say today. I just wanted to give an overview of this existence theory for three-dimensional fully localized solid true waves, and at the same time give you an idea of some of the ways you can use to overcome some of the key difficulties in the water wave problem. So that's it. Thank you very much for listening.
Okay. Comments or questions, please? In fact, I have a question, at least one, which I remember. You said that you can find solutions of original problem as a perturbation of solutions of nonlinear Schrödinger. Yeah. But you consider various symmetric, radially symmetric solutions of nonlinear Schrödinger. But it has many other types of solutions with different symmetries.
Yes.
No, trivial one is localized in one direction and periodic in other, and so on. But for example, with triangle symmetry or hexagonal symmetry and so on. Is it possible to see such solutions of your problem?
Yes, okay. So that comes to the comment I had at the end when I sort of described my theory as self-improving. What you need is to show that these solutions to the nonlinear Schrödinger equation are non-degenerate in a certain sense, meaning that the linearizations, the linearization of the problem at that solution has a trivial kernel. Now, that's a difficult thing because many of these solutions aren't known explicitly. You have to prove it via complicated methods. And for the solutions I showed you, it is true that the kernel is trivial in spaces of symmetric functions. Now, if you could prove such a result for the types of solutions you're talking about, then I could incorporate them into my theory, yes.
Okay, I can point you out a paper by myself in collaboration with Professor Lerner, Lerman from he is a specialist in dynamical systems, and Petr Naryshkin, my former student. It is available in Arxiv. We give the variational method of unified variational method to prove the existence of this equation and many similar equations with different symmetries. And since it is unified, maybe it gives opportunity to show non-degeneracy also in a unified way.
That could be interesting. I should say also it's actually possible to present the whole theory I did today in a variational manner as well. So there could be an alternative way of embedding the results which you're talking about into the theory. So today I presented a kind of the most direct way I know, but you can do the whole thing variationally as well. So this could also fit in with what you say. So I'd be very, very grateful for the reference, yes.
Okay, thank you. Okay. Okay, please, more comments and questions. Well, okay. Thank you once more.
Thank you.
Yeah, I see here also a guest from Sweden. Yeah.
Hi, Mark.
Oh yes, hello Evgeny, how are you?
Good. How are you?
Здравствуйте, Жень.
Добрый вечер.
Well, okay, the next meeting is the next Monday, and I would like to add that the announcements about our future meetings will be put at matnet.ru. Мы, наконец, смогли обеспечить помещение, кроме нашего стандартного сайта, и, естественно, ссылки всем тоже будут даны, но мы еще теперь будем помещать анонсы на matnet.ru. Окей? Thanks. Stop recording.
Thank you. Bye-bye.